Sorry, I was speaking on mute. Hello and good evening to this lecture on machine learning. Um, Today we will be talking more about naive Bayes, and we will gradually shift our focus from naive Bayes to logistic regression. And if possible, if time permits, then we will also talk about how to find the optimal set of parameters using an algorithm very famous called gradient descent. Right. So, as always, we'll start with the question that was given popularly in the GATE CS exam, which is like syllabus common to GATE CS. This is a question on data structures and algorithms. Maybe I will give you guys about 5 minutes to solve this question. Five is a lot of minutes. Whosoever has answered the question first, I will stop there. So make sure you are able to answer this question. It's not very difficult, guys. So make sure you are well aware of it. This is a very simple question, so try this out. So to solve this question, you will have to think through about how. So one way is to you can draw the BST, can draw the binary search tree given these numbers, and then find the in-order tree, in-order traversal sequence. Another thing that you can do here is something very simple. Now, in a BST, as you know, in a binary search tree, the in-order traversal is in a sorted order, right? So if you just sort these numbers out, the numbers that are given, then that should also give you the answer. You do not have to create the binary tree. So that is why option C will be your correct answer. Okay. So this was a trick question. You can go ahead and draw the tree. That will take a lot of time. Make sure you know this. For a BST, the in-order traversal will yield the sorted order binary tree. So since we know motivated about, let's start the lecture. Two lectures back, I taught about something called naive Bayes classifier, which means if I have, let's say, if I write the equation P of y given x is nothing but proportional to P of x given y multiplied by P of y. Okay, y could be any class. I'm not considering that. That's not important for now. So naive Bayes talked about that to model the posterior probability Py given x, given the prior Py, then you can model this P of xy as a probabilistic distribution with a given set of parameters theta. Okay, if you consider a binomial distribution, then typically you would have something like n choose small t, theta to the power t, theta to the power n minus t, and then you would maybe estimate theta from this. And we already looked into this, right? So what we do here is we assume the distribution of data and then we try to fit a probability distribution that fits that data perfectly. And once we do that, we do calculate our posterior probability, which is Py given x. What do I mean by saying it is? Let's take a set of points in the plane. Okay, sorry. Let's take some points on the plane. Okay, let's color it in a green color. So what naive Bayes assumes is it tries to find out the distribution across each dimension, right? Across each dimension, and then tries to find the merge, the multiplies these two distributions to find the final merged distribution. So once you have a model ready for this P of xy, once you have some form of distribution that is present in this example, let's say the distribution finally that you get is something like a multivariate Gaussian. Let's assume, okay, a multivariate Gaussian, something like this, okay, something like this. Then what else you can do? Now what you can do is, given a y, given a class y, you can use this P of xy to sample new data, correct? To sample new data, right? That is the best part about this naive Bayes classifier, because if let's say you are looking at cancer data set, whether a person has cancer or not, okay, it is a very highly imbalanced data set. Why? Because in your data set, typically if you have, let's say, 1 million rows, most of them would be people who are not having cancer. Just maybe about 1,000 or 10,000 will have cancer, the data. Because cancer is a very rare occurrence, it doesn't occur very frequently. There are more people who do not have cancer. So this is an imbalanced data set. If you fit any classification model on this, maybe the model could be biased towards predicting the person does not have cancer. So what you can do is you can do something called upsampling, which means you can take all the data of people who are having cancer, let's call it capital X. You can fit a probabilistic distribution P of X cancer given y equal to yes, the people, which means the people has cancer, the person has cancer, and then after we model it, you can sample data from it and maybe try to balance the two classes, correct? You can get new data by using the probability distribution that we try to find here. Okay, so this is the best part about naive Bayes, and that is why naive Bayes is also very popularly called as a generative model. So what is meant by generative model? Generative model means you can generate new data from it, right? You can generate new instances of the data given the generative model. Now, researchers thought that not always do you want to always generate new data, correct? So you might want to, let's say, what researchers thought, well, let's go into an example, then that would be better. So before that, if you guys have forgotten, let's discuss a bit about Gaussian distribution, which means Gaussian distribution occurs when you have continuous set of data. All the while in this lectures, we were looking at discrete data. For example, if you have a feature x alpha that is not a continuous variable, but that is not a discrete variable, but a continuous variable. In this case, it's a it's the set of x alpha belongs to real numbers. Then the probability distribution function of the given class x alpha given a particular y is nothing but the normal distribution having a mu and a sigma square alpha c. What does this mean? So let me be a bit more specific. So it means given a class y equal to c, so given a class y equal to c, the set of points x alpha that you have, which means all the set of points you have in x alpha, given that class C, what is the mean, which is given by mu subscript alpha C, and what is the variance, which is sigma square, given alpha C, correct? So what does it mean is, we are trying to model the x alpha as a Gaussian distribution, correct? As a Gaussian distribution, where your mu alpha C is nothing but, you take all the points in your data set which belong to the class C, and you take a summation of I equal to 1 to nc, or maybe sorry, I equal to 1 to n, I equal to yi equal to c xi alpha. What does it mean? This means that, okay, sorry, this should be alpha. One second, guys. Yeah, so this means alpha. So mu alpha c means 1 by nc. So let's define nc. Nc is something very simple. Nc is summation of I equal to 1 to n indicator function yi equal to c, which means indicator function or I of x will be 1 when x is true, else x is false. So it will look at all the data points from I equal to 1 to n. C, whichever of them has a class of C, it will just try to add all that, and that will be your NC. So if you want to take an average over all of NC, then you will have 1 by NC, summation of I equal to 1 to n. If that yi, the label belonging to the xith sample, is C, then you will just add the corresponding value alpha to this summation. Okay, just the mean formula, nothing very fancy here. And the variance sigma square alpha c is nothing but, again, 1 by nc, right? Summation I equal to 1 to n, I of yi equal to c, and xi alpha minus mu alpha c whole square. Okay, fine. So this is just a standard formula for the Gaussian distribution, and the probability density function for the Gaussian distribution x alpha given y equal to c is nothing but 1 by root over 2 pi sigma alpha square e to the power minus 1 by 2 x minus mu alpha c divided by sigma whole square. Correct? This is the probability density function for the given normal distribution that we assumed. Now, what we will do is, once we have taken this distribution, then we will try to derive the Gaussian naive Bayes formula given our assumption of this distribution. So what do I mean by it is, if our given function, let's say all functions are given that they follow a Gaussian distribution, so given a probability sample xi equal to small x such that the yi equal to small y, given a simple probabilistic sample here, and y, let's say yk or class k, it means the probability density function is 1 by root over 2 pi sigma I k square e to the power minus 1 by 2 x minus mu ik by sigma ik square. Okay, there are many ways. This is just the same thing that I wrote earlier. Okay, so what happens here is what we will assume. We'll do some assumptions before I start the proof. So my first assumption is that probability of, we have two classes 0 and 1, and we assume that the probability, the prior probabilities, right, p of y equal to 1 follows a Bernoulli distribution with a given probability pi, such that the probability of y equal to 0 is nothing but 1 minus pi. Correct? This is my first assumption. The second assumption that I will do is to simplify the things here. The standard deviation across both the classes is the same, and I will consider it as a sigma I. Okay. Okay. So we'll have these two assumptions just to simplify things. Okay. Now let's take a very particular class where p of yi equal to 1, right? Given xi. So to avoid this, I will write similar notation p of 1 given I. Okay? Just to simplify things, okay, so that it doesn't look very cluttered. 1 means the class is 1 given xi. Okay, right. Or let's just write this as x. That should be okay. P of 1 given x. Okay, just a single data point. I want to estimate the probability of P of 1 given x. This is the posterior probability, that is after considering the prior probability. Okay, so how we will do it is, if I apply the Bayes rule, right, I can directly apply the Bayes rule here and say that this is nothing but equal to probability of x given 1 multiplied by the probability of 1 divided by the probability of x given 1 multiplied by the probability of 1 plus the probability of x given 0 multiplied by the probability of 0. This is just a standard Bayes rule we have followed. I hope that I don't have to review this. That should be simple for you guys, right? What I can do is I can divide the above and below expression by p of 1 into p of x given 1, right? So what I will get is 1 by 1 plus p of 0, p of x given 0 divided by p of 1, p of x given 1. It's just dividing the numerator and denominator by the p of y given equal to 1, p of x given y equal to 1. Okay. Now, as we all know that we can write x as e to the power ln x. Okay. Why we do that? Hold on. I will explain. This is part of the proof here. So, but for hold on with me now, I will just go through this one again, step by step. So 1 by 1 plus e, let me call it as exponent. You can write just for clarity. Exponent of log of, I can write this entire thing, p of, sorry, p of 0 given p of x 0 divided by p of 1 multiplied by p of x given 1. Again, what did I did till now? I did nothing here. I just took one sample of the probability function of the prior probability, which is sorry, I just took one sample of the, I assumed, first of all, I assumed that my feature follows a Gaussian distribution with a given mu and sigma. And then I modeled the fact that the prior probability comes from the Bernoulli distribution with P of 1 having probability pi and P of y equal to 0 having a probability 1 minus pi. And my assumption was that the standard deviation across both the classes are the same. That is sigma I0 is equal to sigma I1 is equal to sigma I. And if I want to find out the posterior probability, which is P of yi equal to 1 given the price xi, I simplified it by saying P of 1 given x. I first applied the Bayes rule that states that P of x given 1 into P of 1 by P of x given 1, P of 1 plus P of x given 0 by P of 0 into P of 0. Then I divided the numerator and denominator by P of 1 into P of x given 1. So we get 1 by 1 plus P of 0 into P of x 0 given 0 by P of 1 given into P of x given 1. Okay. So once I did this, I applied the property that x I can write it as e to the power ln x. So I've just written the entire denominator, that section, which is p of 0 into p of x 0 given 0 by p of 1 into p of x given 1 in the part of e to the power ln this. Now what I can do is there's another property of log which states that log of ab is nothing but log a plus log b, or ln, whatever you can call. Ln is just log base e, so 1 by 1 plus exponent of, I can write this as log of p0 by p1 plus log of p of x given 0 by p x given 1, right? Okay, don't be stumped that how can I how can I separate the fractions? No, you can consider p of 0 by p of 1 as a, and p of x given 0 and p of by p of x given 1 as b, and ab will give ln a plus ln b. Okay, why I'm doing this all I will explain. Just hold on for some time. Okay, things will be much more simpler with as time progresses. So I can write this as 1 by 1 plus exponent of ln t of 0. I can substitute the value from a Bernoulli 1 minus pi by pi plus ln. Now what I can do here is, since we know that naive Bayes has conditional independence, which means given a class C, a probability of x given that class is nothing but I can take the product of the individual probabilities. So I can write this as nothing but ln of pi I. Sorry, let me not say this as pi I. This is nothing but product of I. I'll write just as this form. Okay, it shouldn't confuse you. It means the product of all I across p of xi given 0 divided by p of xi given 1. Okay. Now, if there is a product, you can obviously take something called a log, and there's already a log outside this, right? So for a product of log of some product can be summation. I can write the summation, which means this is nothing but equal to 1 over 1 plus e to the power log 1 minus pi over pi, right? Plus summation, because it was log of product, so you can become summation of ln p of xi given 0 divided by p of xi given 1. Okay, with me till now? Good. Now, we know that since p of xi given any yk is nothing but 1 by root over 2 pi sigma ik square e to the power minus 1 by 2 x minus mu ik by sigma ik square, right? This is the probability density function for a normal variable, and our assumption was that the standard deviation across different classes are the same, and we considered that as sigma I, correct? Which means sigma 0 is same as the sigma 1, and I consider that as a sigma I. Okay, so I can substitute these values to the equation that is given, and maybe I'll just zoom in that equation, exponent of that. I will just look at that here. Okay, and if I write that, then it is nothing but exponential of ln 1 minus pi over pi. Okay, maybe what I will do is I will just use a different color. Maybe I'll also remove the exponent for now. Again, these are present, but just to simplify things, I will remove them for now. So, and I will also use a different color to highlight some very important observation here. So ln 1 minus pi by pi plus, again, you can do the math. That is not very simple. I'm just writing the final result, mu I 1 square minus mu I 0 square by 2 sigma I square. Again, this is very easy to derive. You just put the formula there. Okay, I'm not doing that, guys. I hope that is easy for you to do. Plus, now here is the interesting part. I can write this as a summation over all I, mu of I0 minus mu of I1 divided by sigma I square xi. Now, with this equation that I have wrote, I have color coded it because that is the hint here. If you see very carefully, there is something that I want to say here. Okay. If you looked at the perceptron model earlier on, we had an equation called y equal to w transpose x plus b, correct? So if I consider this as my xi, which is the x I am considering, so let's write this as x, not xi, x, then if you can see that, oh sorry, it should be xi only because it's the your so you are equating over all the data points, summing over all the data points I. So if you have this, then can I call this as my W, right? I can call this as my W, okay? Maybe not the summation inside, not the entire summation, but just the part inside of it, which is this part. I can call this as my W, correct? And let's call it Wi, okay, just for simplicity. And this part over here is the constant part, which is not dependent on xi. So can I call this as the b? Now see, wi xi summation plus b. What is this? Nothing but w transpose x plus b, right? It's a dot product. Wi xi is same as w transpose x plus b. So, and also another thing that I can do here is I can absorb the B's as well, but I won't do that for now because again, so this is a very interesting part here, right? So I hope you're trying to understand where I'm getting to. So now the P of y equal to 0 given x will be nothing but, oh sorry, P of y equal to 1 from the earlier equation, right? So deriving P of y equal to 1 given xi, so is nothing but 1 by 1 plus e to the power b plus summation of I wi xi, right? And if I have this, then P of y equal to 0 given x is nothing but 1 minus P of y equal to 1 given x, right, guys? So this one is nothing but e to the power b plus summation of I wi xi divided by, right, divided by 1 plus e to the power w0 sorry, e to the power b plus summation of I wixi. So what I can do now is I can take uh, I can divide the two terms p of y equal to 0 given x divided by p of y equal to 1 given x as nothing but e to the power b plus summation of I wixi. Okay, now this will be the best part of the entire lecture till now. Okay, so what we will do is we'll take the log on both sides. So log of p of y equal to 0 given x divided by y equal to 1 given x is nothing but log of e to the power is nothing but the same expression itself. So b plus summation of I wixi. Now please focus on this equation very carefully. I will write a simple thing here. So log x, right? Everyone knows log x is not defined for x less than 0. And everyone also knows that when, sorry, the log x, the sign of it, okay? When is log x negative? When the log x sign is -1, when the x lies between 0 and 1, correct? It is 0 when x is 1. It is 1 when x is greater than 1. Correct? This everyone knows log. Now equate that to something here. If my p of y equal to 0 given x is greater than p of y equal to 1 given x, what is the sign of the equation on the left hand side? The sign of the equation on the left hand side will be greater than 0, correct? Because log of value greater than 1 will be greater than 0. So can I also say that my b plus summation of I given wixi should be, if it is greater than 0, then I can predict that it is of class 0, then it is class 0. And now think of the other scenario. When the probability of y equal to 0 is less than x, then b plus sigma I wixi will be less than 0, correct? So that they can be equated. So then I can say that it belongs to class 1, sorry. So what can I say from this? Can I say this b plus w summation of wixi is nothing but what? Is nothing but our decision boundary, right? So b plus summation of I wixi forms our decision boundary. And what does this also convey? Can I say a very important result from this one, that naive Bayes is actually what? Is actually a linear classifier. Okay? Now, because if you see the linearity nature of this sign, there's nothing quadratic in this equation, right? Everything is linear, correct? So that is why naive Bayes is also called a linear classifier. Okay? Now again, let's come back to the equation we wrote for p of y equal to 1 given x. So P of y equal to 1 given x is nothing but 1 by 1 plus e to the power w0 plus summation of I, again, sorry, I think I wrote b here, b here, b plus wi xi. Okay, since you also learnt in the perceptron algorithm that we can also absorb the b by putting w0 as b and xi having a new dimension 1, then what I can do is I can also write this as 1 by 1 plus e to the power summation of I wi xi, which means my wi is the old wi only. I will just add b and my xi will add a 1. I have already talked about this in perceptron. I think that is clear. Okay, fine. Now focus on this equation very carefully. Naive told you that in order to find the best possible answer for the posterior probability P of y equal to 1 given x, you assumed a you assumed a Gaussian distribution for xi, for x, and then try to find out that given that x, what is the probability of y equal to 1 using this equation. Someone came and said, okay, fine. Why don't we do one thing? Let's start from here. Naive Bayes told us to come till here. We are trying to find out a model. We are trying to fit a distribution to our data. Why don't we do something very simple? Let's assume that this is our starting point and let us try to find out the optimal values of W and B. Okay, what was earlier? Earlier we were trying to find out P of y equal to 1 given x by assuming that our P of y equal to 1 or P of x given y equal to 1 or P of x given y equal to k follows a Gaussian distribution. And then naive Bayes tried to find out that this is the best equation that you can get. If you solve this, you will get the probability answer for y equal to 1 given x. But over here, you had to assume the Gaussian distribution having some parameter mu, mean mu, and standard deviation sigma. People try to say the other way around. Let's take both of them as variables. Let's start with this equation, which looks very generic here. And let's try to find out a possible way by which I can minimize this. I can try to find out the best set of parameters W that best fits the data. Okay. So this was a breakthrough in research, right? And this one is also called as the, again, so previously we tried to find out the P of x given y equal to k, and once we had that, it was something called the generative model, because given a particular class k, you can use this probability distribution to sample other data points. In the discriminative approach, what we do is we try to find out, given that data point x, what is the probability of trying to find out what is the probability of the likelihood of occurrence of x, of y given x. So this is also called the discriminative model. Okay, there are techniques that exist to try to maximize this function. One of the most popular technique that we have in the market today is called maximum likelihood estimation. Now, what does maximum likelihood estimation assume is that you are trying to estimate P of y given x. Okay, and how are you trying to estimate? By estimating the parameters w comma b directly. Okay, which means an maximum likelihood estimation also assumes that, and that is actually one important point, your samples are IID. What it means? Your samples are identically and independently distributed, which means the probability distribution from where you try to sample your data points, okay, this probability distribution is IID. Each sample is not dependent on any other sample, and they are all from the probability distribution. That is assumption. So if you say they are independent, what I can also say is that MLE tries to find for what values of w comma b, which is Rmax of w comma b, is the product of each data sample from I equal to 1 to n. The probability given that w comma b, what is the probability of that occurrence of class yi given a particular xi w comma b. This is the assumption. Okay. Now, one natural thing that you might assume and you might think here is there's a product, and whenever we see products, we try to find out the log, right? So I can write this as, okay, just a minute. I think I'm writing somewhere and it is written somewhere. Okay, fine. So, okay, just a minute. Okay, fine. So, yeah. So I can write this as Rmax w comma b summation, because I'm taking the log now, log of p yi given xi. I'm not writing w and b because those are repetitive, but it means the same thing. Okay. Now, what I can also say here is that this is nothing but Rmax w comma b summation of I equal to 1 to n. Again, I am doing one other assumption that my each yi is the two classes either -1 or +1. Contrary to what I assumed earlier, it is assumed that classes are either -1 or +1. Okay, this is my other assumption. Argmax of log 1 by 1 plus e to the power minus w transpose xi into yi. Okay, we have seen this equation already in the perceptron model, so I'm not explaining here. If you want to understand why I put the yi there, then please look at the perceptron model video. That doesn't make any difference in this scenario. Okay, because if yi is equal to 1, if y is equal to 1, again assume, again see one more thing here. Okay, I have put a minus here, contrary to my previous example where I was putting a plus. It was e to the power w transpose x, because I was trying to prioritize the negative class. If I just flip the sign, which is if I add a minus sign, then I try to find out that given, so I will try to find that p of y equal to 1 is my priority class in this case. Priority class in the sense the class that I want to predict for now. So if my w transpose xi is greater than 0 and my yi is 1, that's a correct prediction. So the equation remains as it is. If my yi is -1, then my w transpose xi should also be negative because of the equation, and then also it's the same thing, right? It's the same thing that I wrote earlier, just a little bit twist. Again, for more explanation, please look at my perceptron model that explains it much more detail. This one I can write this as Rmax summation of I equal to 1 to n. I can write this as log 1 minus log of 1 plus e to the power minus w transpose xi times y. Now, I hope every one of you know log 1, the value of log 1 is 0, right? So it boils down to R max w comma b minus summation I equal to 1 to n log of 1 plus e to the power minus w transpose xi times yi. Okay, now what we will do here is I will try to give you a small short break, and the break is not actually chilling around. Okay, we are actually trying to study here given the time as well, which is not very much you have before the exam. What I will try to ask you, just beat your head whatever you learned till now. You must have taken notes, just try to revise them out, and we will meet in 5 minutes where you will have to come up with an estimation of, if you want to maximize a function y equal to log x, how can you do it? Okay, and if I give you a small hint, again that hint might not work, guys, let me be very clear. Okay, don't go and tell that Aditya is telling how to maximize log x. It might happen. I think that's why I answered the question actually, but still, okay, we learned something called maxima minima in our 11th, 12th, maybe in your engineering, maybe much earlier, maybe much later, maybe now. Okay, so maxima minima, you can try to find the maximum value for which the function value is maximum or minimum. Take some time, take 5 minutes, okay? Maybe answer this question, try to beat your head around. What will be the value of x for which log x is maximum? Can you tell me the answer for it? I will give you some time, okay? Try to find out using maxima and minima and let me know the answer, okay? Bye. Okay, anyone who wants to volunteer? Ah, come on. Let's give you a hint. Hmm. See the thing I wrote on the top right about log x. Hmm. Is log x defined when x is equal to 0? So why am I saying log x equal to 0? So if you have learned your maxima minima in your childhood, okay, then what you can do here is you can do something like dy by dx or differentiate y with respect to x and equate it to 0. Okay. Now if y equal to log x, does not exist any value of x. There does not exist any value of x because x is always defined greater than 0, right? So there does not exist any value of x for which value of log x will be the differentiation of log x will be equal to 0, right? Since log x is defined for a positive number x, then g dash x is also greater than 0 for any x. So you cannot find any value for which g dash c is 0. Hence we can see that the function does not have any minima or maxima. Okay. So now we are stuck at a point where the MLE is P of y given x is argmax I equal to 1 to n log of 1 plus e to the power minus transpose xi. We were here and we now find out that we are not able to maximize this function. Okay. What can we do? Good, good, very good. We can convert it into something called a very good. So we can do something called a minimization problem. How to convert it into minimization problem? Yeah, we just take the negative. Good. So P of y given x is nothing but now your max becomes a main problem. I equal to 1 to n log of 1 plus e to the power minus w transpose xi yi. Okay, fine. Okay, now we are at another problem, right? How do we actually minimize it? Correct? Ah. So this is the very big essence of machine learning which we're learning today, which is what we do is in machine learning, we formulate something called a loss function for a given set of parameters w. Okay, in our case, we'll just write this one as our loss function, the function that we are trying to minimize, our min of w. Again, I'm sorry guys, I think b should not be there ever because we try to encapsulate it, right? So I equal to 1 to n log of okay, and what we try to do is we try to minimize this loss function w. Okay, so what one of the main criteria, one of the best part about this equation, which is this equation here, is that it has two very salient points. One is it is differentiable. I hope you know what you mean by if a function is differentiable. And the second part is this function is convex. Now, what do I mean by a function being convex? It means given this graph, the function is like this. So for a given w, this is my loss Lw. I might have any initial loss, let's say W0, and my goal is to try to come back to here. So if function is not convex, then what happens is the function could be something like this. Okay. In that scenario, if I start here, I might land up and say this is the minimal value for which my loss function is minimum. But as you can see, it is not this one. It is actually the value here, which is a W here, not the W that is given on the top. So these local minima is not possible when it comes to a convex function, where you will always get the global minima. Okay. So if you know these two properties, then we will have some way to find out how we can estimate this loss function for a given set of parameters W. Okay. Now, how do we do that? So what we do is, we follow something called a gradient descent approach for minimizing this problem, which means what we do is we have our loss of W, which denotes the loss function. And what did I tell you some time back? I told you that this function is differentiable, right? So let's say G of W denotes the gradient of the loss function W. Okay, loss function LW, sorry, loss function LW, right? And then what I do is I update my W plus some vector S. And I claim this vector S when it comes to gradient descent is nothing but minus alpha GW. Okay. For now, forget about alpha. Let's say alpha is 1. Okay, forget about it. And my S is for now, let's say alpha is 1. Let's assume. Okay. Then what happens is, then my S is nothing but minus GW, which also means I'm going in the opposite direction of the gradient. How? See, very interesting. This will be, just follow with me. So let's draw the function for given W, the loss function LW. Let's say this is the loss function, right? And I start with some W0. Let's say this is W0, which is my first value of the loss function. Now the gradient also means the slope of the tangent passing to the line, right? Right? And the gradient at this point will be what? Positive or negative? The gradient will be positive or negative? The gradient is negative, right? The slope is downward. It's negative. So if the gradient is negative, then what I'm doing here is, uh, I'm doing the negative of the gradient, which means if the gradient is negative, then negative and positive. So I'm increasing the value of W by GW, right? So if I increase the value of W, then maybe I land here, somewhere here, from here to here. So see, I'm coming closer to the goal, right? On the other hand, if you look at the other side as well, let's assume that you start from here. Okay, then again, this is the line tangent. Again, this might not be absolutely correct, the tangent, but please bear with me. I hope you understand. And the slope here is positive, right? And what I'm trying to do is negative into positive is negative. So I'm trying to reduce the value of W by some by GW as well. Okay. So I hope you understand this. That's how this thing is done. Okay. Now, I will not tell you now. Maybe I'll give you some time to think Just think, why is the need of an alpha here? What will I have if I don't have alpha? Just think of a scenario where what is the need of the alpha? Without the alpha also we are able to find out, right? I just told you how to find. So what is the need of alpha? Try to find out. Try to think for 2 minutes and then let me know. Yes. So as I said, no problem. It's okay if you don't understand this. If you didn't understood it, it's very simple actually. So S prime is minus alpha times G of W, right? Where G of W denotes the gradient of the loss function LW. And so let's take a scenario where your loss function, the graph, something like this. So your slopes at this point is too high, right? If you see it's very steep, right? So what will happen is if you don't have an alpha, or let's say the alpha is 1, then when you try to add the value s to your current vector w, so w of n plus 1 is nothing but whatever is the current value of w plus s. It might happen that your new s is this, new w is this, which is still not the minimal. The next time when you go here. Next time when you go here. Okay. To slow this update a bit down, what we do is we use the learning rate, which is the alpha. Alpha could be, let's say, 0.1. So instead of jumping so much, I will only jump still a little bit. Maybe I jump till here. Then I jump here. Then I jump here. Then I jump here. And then I find the minimum. So alpha is used to control the rate of updates. But now you might think that my alpha, I could make it very small. Again, if you make it very small, let's say baby steps, you went here, then 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 what happens is it the updates are very, very slow and it will take a lot of time to converge. So you need to have a good balance between the learning rate. Again, depending on the learning rate, there are different variations of the gradient descent algorithm. For example, ADA-GRAD is one very popular algorithm, adaptive gradient descent. Another one is called, there's one more famous called momentum descent, okay, which is the first you will increase the gradient by a huge amount and then gradually you will try to decrease it, right? Okay, maybe, yeah, you will try to decrease it. And there are other ways as well. Again, the GATE exam only mentions that gradient descent is there in the syllabus. So I'm not very sure whether the types of gradient descent are there. But once you get a rough funda of what is gradient descent, I would suggest you, then things will be very simple, right? You can just go ahead and look at them in a very good blog as well. So, and I will share you a video as well later on. That's fine, but I'm not beating around that for now. That's not very difficult to understand for now. Okay. So, okay. So the last part before I end this lecture for today is actually I will give you an algorithm to do gradient descent. Okay, we just try to find out how to find out the gradient descent. I'll give you an algorithm. So the first step is to choose a starting point W0. Which is your initialization. And what will you initialize? Your W, right? You can't initialize the loss function, right? Or else you can initialize it at 0, correct? So you'll trying to find the value for which minimizes the loss function. So you'll initialize your input parameters, which is W, let's say W0. Then the second part is you will try to calculate the gradient GW, which is the gradient of your loss function LW. And then step 3 will be to update your W as W plus S. So sorry, W of n plus 1 is W of n plus S, where S is minus alpha GW, where alpha denotes your gradient, your learning rate, right? And 4 is, so alpha, let me write down here, is your learning rate. And the fourth step, final step, is to repeat steps 2 and 3 until there are two options here. One option is you can run it for a set of fixed number of iterations, let's say 1000 iterations. Or you could fix it as running for 1000 iterations, but if your loss function of W of n plus 1 minus the older loss function n is less than or equal to some epsilon that you, or tolerance limit, if it is very, very small, very, very small, then you can also say that you will terminate the algorithm, because there's no point going beyond that, right? Going to optimize more than usual. You can maybe do that, but these are different ways to um, um, try to find out the right value of the loss function. Okay. Sorry. So so this is the algorithm that I talked about how to do gradient descent. Okay, we have some time. I won't leave you guys for now. What I will do is maybe again read through the notes. Try to, if you have any doubts, feel free to ask. Okay, this is, I know this is not very easy for a beginner, but if you understood the math behind it, if you have some background on calculus and all that, it will be very, very simple. Just read through once again. Try to ask me any doubt you have. It could be anything, guys. There's nothing called a silly question. It should be as simple as possible. Meanwhile, I'll just try to find out some questions that we can also discuss after this call. Okay. So maybe try out these questions. Okay. Try out these questions and try to read the notes. Okay. Because the questions will be based on today's lecture only. This is for you to better understand the things, right? So these questions are interview questions, because this is the first time gate BA is happening. So obviously I won't have any gate questions. So maybe try it out, okay? And let me know what it is, okay? Okay. Any questions? Okay. It seems like you understand everything. So the first question that I would maybe ask you is, can you think and tell me what is the difference between a cost function and the gradient descent? Again, let me remind you guys from the previous lecture. A cost function is nothing but a loss function applied on a set of data points. A loss function is for a single data point, while a cost, I think I should have called that a cost function. I'm sorry about that. A cost function is something that is defined over the entire training set. So what is the difference between a cost function and gradient descent? Correct. So a cost function is something that we want to minimize, okay? And like we saw in the example, and a gradient descent is a method for actually minimizing that said function, right? So that is nothing but the cost function. And the difference between a cost function and the gradient descent. The next question that I might ask you is, can you apply gradient descent on a non-convex function? If a function is I told you an example now that the function is convex, so we can apply gradient descent. So can I say that gradient descent I cannot apply on a non-convex function? Again, if you paid attention in my lecture, then you will be able to answer this. Yes, yes, correct. So it can be applied. For sure, it can be applied. There is no one is stopping you. It's a very generic method for doing optimization. But the problem that might occur is you can reach something called a what? Something called a local minima. Correct. Local minima means some local region of loss. It might not represent the final loss that you might expect it to have, which is the global minima. Okay. Huh. So can I conclude that it is better to use a small learning rate than a large learning rate? So learning rate, the alpha that I talked about, is it okay if I use a small learning rate than a large learning rate? Actually, no, because a small learning rate may lead to more problems, may lead to more issues. Okay. Uh, it may lead to more issues. Smaller learning rate, your convergence will take more time. Let's say if you are having a, let's say, what shall I say? Let's say you are having a 1,000 iterations gradient descent, then that is not, your algorithm might not even converge by then. Okay, then you need to have a balance. You cannot have a large running rate. Why? Because you might overshoot the minimum, right? Okay, okay. So these are some questions that were there. We'll discuss some more questions, some true or false. Okay, I'll put them on the chat. First question is logistic regression a supervised learning algorithm? Oh, come on, guys, very simple. Although the name sounds like it. Huh. Yes. Yeah, obviously it's a supervised learning algorithm because we are also considering the labels, right? Now, is logistic regression used for regression? Name is logistic regression, so it should be right. Yes. Is it used for regression? No, don't confuse with the name regression. We'll look into it why it is still called regression in the next lecture when I talk about linear regression. But logistic regression is a full classification problem, not a regression problem, and it is false. Next is it possible to apply a logistic regression algorithm on a three-class classification problem, which is the value of k is now 3? Is it possible to apply logistic regression on a three-class problem? Okay, so it's a very good question, and this requires some thinking because I have not taught you, right? So what you do here is for a three-class problem or any class problem, let's say any k class problem, there is something called a, so your data set might contain some data of class 1, some data of class 2, some data of class 3. There is something called one versus all approach, where you first consider only class 1 and then class 2 and 3 can be considered a single class. So you try to estimate the model given this scenario. Then in the second case, what you do is you try to say class 2 is the main class and try to estimate the model given merging by merging class 1 and 3. In the third scenario, you take class 3 as a main class and try to find a model where class 3 is the main class and 1 and 2 are merged to have one class. Then you have three different logistic regression models for C1, C2, C3. Then you find the corresponding predictions for C1, C2, C3, and then try to find the maximum loss, maximum of the three to find the correct answer. That is C1, C2, C3. That's why it's called one versus all approach. Okay. And another thing of logistic regression is since it's a linear classifier, your data is assumed to be linearly separable. If there was a perceptron algorithm, then you might know that the perceptron algorithm will never even converge, it will loop on forever. But that is minimized in case of logistic regression because it might stop at a local minima or global minima that it finds the best. It tries to find the best fit for the data. It will not happen that it will absolutely stall. Okay, and one last question, maybe I will write it here. Look at this graph here that I draw. Yeah, can you tell me how many local minimas are there in this graph? How many local minima are there in this graph? Correct. So there are four. One, two, three, four. Because I might start here and I might come here and say, okay, fine, my loss is not decreasing now. So I can say that this is my minimum, or I may start here, come here, may start here. If I come here, then that's a global, that's the best case. It might happen that I start here, my update brought me in the second region, and then I come here, or it could be the other way around as well. So there are four local minima and one global minima. Okay, these are some functions that we have. Again, in the next class, we will also solve some few questions formally. This one was just to maybe we had some time. That's why I tried to discuss the functions, discuss some questions that might help you strengthen your concepts. In the next class, we will look at linear regression and something called regularization that helps you to stop something called overfitting in a linear regression model. Then after that, in the next class only, I think most probably we will try to find out the we'll try to find out the we'll try to find out for the next in the next class we'll try to also look at bias variance trade-off, which is one of the most important topics in the lecture. Okay, fine. So that's all I had to say. Maybe I will stop recording, and if